Okay, so today we are going to talk about generative models for graphs. And again, we are using the slides from this Stanford course, Machine Learning with Graphs. And this is their course website. And on their website, you can find the full slides. Of course, these slides I have modified a bit to fit meetup better, but you can see the full version of the slides, and you can even see the homework there if you want to have some hands-on practice on this topic. So first, on the motivation for graph generation. So for all the previous meetup that we have talked about, we mainly directly learn from graphs, right? So we assume the graphs are given, say the social network that people connect each other, say on Facebook, and economic networks like telling about how companies are, transacted or collaborated with each other, and also the communication network. So all this network kind of already exist, and we just directly train models on these existing graphs to solve certain problems. And this meetup, we are going to focus on how are these graphs generated, right? So we are not just directly say, okay, the graph is given for granted. We just take it for granted. But we are more like looking into graph on the formation process of these graphs, on how these graphs are generated. So we want to generate realistic graphs, right? So, well, one a good test to see if our assumptions or if our process makes sense, we directly just generate a graph. Say we call it a synthetic graph and compare it to real graph to see if they are very similar. If they are similar, then we say, okay, that assumption or that process makes sense. And that is actually the underlying process that generate the real world graph. So the goal of this is we want to generate the synthetic graph, and we want to make it as similar as possible to the real graph. And there are many applications of this, such as drug discovery or material design, where we want to find a new particles or new molecules, right? So the molecules are kind of a model-less graph. So you want to detect a new graph that potentially can lead to very good, say, drug property or very good material properties. And also we can use it for social network modeling, and it can help tell us how the social network forms, like the community groups are formed, and how the social network is going to evolve in the future. So why do we study graph generation? So first, of course, it gives us insights, right? So if we can generate very similar graphs to the real world, then we can understand the formation of the graphs, like how the community graphs or how the community groups are formed over time and how they are going to evolve in the future. And again, how they are going to evolve is related to the prediction, right? So we want to predict how the graph will evolve further into the future. And we can, if we are able to generate graph, we can do a lot of simulations, right? We can use the same process to generate novel graphs that never exist in the real world before. So that's very cool, but it still can be realistic and can be helpful, just like the drug discovery. And also for the anomaly detection, right? We can decide if a graph is normal or abnormal. So if we so if there is assumption made and we are able to generate lots of graphs from that, and if say we observe a graph that is impossible to generate or from the model that we assumed, we can think that the graph is abnormal, right? So it's not up to our expectation. So it can be used for anomaly detection as well. On the history of graph generation, and actually in the Stanford course, if you look at their course content, they actually have some lectures on, say, the properties of the real-world graph, right? So we want to have graph models that should fit these properties. So one popular property, say, the degree distribution, right? So you just count how many neighbors each graph node has, and you got a distribution. And then you want to have a graph generation model that match with this degree distribution. And then they also talk about the traditional graph generating models, right? So each will come with a different assumptions. Say, I want to have, like high clustering coefficient or low clustering coefficient graph. And also they introduce a small world models, right? So each of those traditional models actually comes with some assumptions and comes with, say, some target, and then and they propose some process to generate the graphs. Well, the deep graph generating models is a little bit different. So it's I think it's fully data driven, right? So it's it will directly learn the graph formulation process from the data, and actually that formulation process can be very complicated. And it's very hard to be formulated, but it can be approximated by the deep learning network. So this is the focus of this lecture, this meetup, right? We are going to look at the deep graph generative models. So far, we have looked at the graph neural network, right? The graph convolutions. So the graph convolutions is kind of just for each of the node, it's going to aggregate the messages from its neighboring nodes, right? And then pass through some activation functions. And you can also use all kinds of deep learning tricks to do the regularization or dropout. And you can add another layer of graph convolution, etc. And in the end, you are going to get a node embeddings that represent the graph information. Let me. Okay. So in the graph generation, you can think of it as deep graph decoders, right? So you have some desired properties, so you have some information where you want to work it backward into these graphs, right? So the output of your model will be actual graph. Okay, so that is the basic introductions of why we need a graph generation and what is a potential application of graph generations, and a brief history and what is the final model output of the deep graph generation. So any questions or comment so far? Okay, if not, then we are going to look into the actual process for the graph generation. So in the graph generation, there are usually mainly two tasks. So one task is to generate realistic graph generation, right? So you are basically have a training set. Say you have a training pool of actual graphs or the actual existing molecules, and then you want to generate the graphs that are similar given that set of graphs, right? And that is the focus of this lecture, of how can we generate similar graphs given a set of graphs in a training set. And the second goal, I think, is also very interesting, is the goal-directed graph generations. So not in addition to generate realistic graph, you also want to optimize the graphs given certain objectives or constraints, such as in the drug discovery process, you want to, say, improve the drug score, right? The drug necklace, or reduce the toxic or the toxic degree of the drug, right? So that is kind of your objective. You also want to optimize along with this realistic graph generation. And actually they use reinforcement learning for this, but we are not going to talk about that. Maybe it's a good fit for separate lecture on this. So in today's meetup, we are mainly focused on how can we generate a graph given a set of graphs in the training set. So about the generative model. So first, we need to understand what is a generative model. Say we observe some graphs, and we can assume that the graphs are sampled from some distribution. Say the ground truth distribution is the p data G, so it's a distribution for the graphs. Right? So you can assume it's the p data distribution. And actually, we want to train a model distribution. So this model can be a deep learning network, right? To approximate the p data as much as possible, and as close as possible to the p data distribution. And once we have this p model, we can sample from this p model, and that gives us the way to generate new graphs, and at the same time, very similar to the graphs that we observed in the p data. Right, so here is the p data distribution, and we want to learn a p model distribution that is very close to p data. And then later on, we are going to sample from this p model. And the aim of that is first, since it's a sampling process, right? So it gives you some randomness, and that randomness brings us new graphs. And at the same time, since these two distributions are very close, and then the generated graph should be very similar to the graphs that we observed. So in the setup, usually in the generative models, so usually there's again the data distribution, which is never known to us, and so it's just not possible to have a closed form of the data distribution. But we have these observations xi, right? So you can think each of the xi is a graph, and these are the samples from the p data distribution. And then we assume, and we want to train a model, a p model, with the parameter theta, and theta is the parameter we want to learn for the model. And then we want to use this p model to approximate p data, right? So to make it as close as possible. So there are two goals in the generative model. So it's not just for graph generative model, it's actually for all kinds of other generative models. There are two goals mainly in this type of model. So the first goal is to have this p model as close as possible to p data. So this goal is about a density estimation. And of course, we want to adjust the theta so that the p model is close to p data. And the second goal is that we want to make sure that we can sample from the p model. And this is a sampling process. Right? So we are able to generate the graphs or samples from the p model. Okay, so for the first goal, how can we make a p model close to p data? The key principle they use is called a maximum likelihood. Right, so it's basically so this is the parameter theta, and this is the x. X is kind of the observation that is already observed from the p data model. So you want to maximize the likelihood that find the parameter theta such as it gives you the maximum likelihood for all the observed data. So you sum it across all the data. So basically you sum it across all the data points you observed and maximize this likelihood for all the observation. So you will figure out what is the best parameter theta so that you maximize this likelihood function. So that's the first goal, right? So we want to find the best theta that maximize the likelihood for all of our observations. And the second step is to sample from the p-model. Say theta, we already find the best theta. And then the next, we need to sample from this distribution. So we want to sample from this distribution. So basically, we can first sample from a noise distribution, and then we use this as the input to this p-model function. And that gives our sample in the end. So yeah, so this is a sampling process. And the main question is, how can we design F, right? So the F is, it can be a little bit complicated, especially if the graphs are complicated, right? So good news is we can actually use a deep neural network to approximate that complicated function and train it using the data we have. So the next is, how can we apply all of these logics to a graphs? How can we formulate the graph generation model? So they call it it's the auto-regressive models. So it's a very common model that is used for model to model sequence, right? So auto-regressive is basically telling you that you want to use the past steps or the earlier steps or the earlier data points to model your current data point. So it's following this a chain rule, right? So it's basically the joint distribution is going to be a product of these conditional distributions. And each of the data points at current time, well, depends on all the observations from earlier time, right? So this is a very popular way to model a sequence. And in the graph generation models, the p-model is used for both density estimation and for sampling. While some other generative models, they use separate models for density estimation and sampling. But here we use the same one model for both goals. And over here, so you can think of this x, the final x is a vector, right? So xt is the tth dimension. If the x is a sentence, say it's a language sentence, xt can be the tth words in the sentence. And in our case, xt will be the tth action in the graph. So that action is add a graph node and add an edge to the graph, right? So we can actually formulate the graph generation process by a series of actions, right? So the action can tell the model, the output of the model will be, okay, add a node and add these edges to the graph. I feel it's really cool, like when you think about, oh, the graph structure can be so complicated, and how can we really, model that graph generation process? And I find this idea, yeah, it's kind of neat and very straightforward to understand, right? So you can just think about that graph generation process as a sequence of actions. Okay, so I will pause here a little bit to see if there's any questions on generative model and what is this auto-regressive models is about before we move on next.
What if you want to add more edges than not one node and few edges?
Yeah, so this include, you will see next. So this add node, add edge means add the edge or related to this node. So each time, yeah, it can be multiple edge, yes.
I understand. So the graph itself is the outputs of all the timestamps, the total graph.
Yes.
I usually saw auto-regressive in connection with time series. Is there any connection here with time series?
Yeah, I think yeah, you can use the same thing for time series prediction, right? So X can be a vector, while the vector will be your time series sequence. And you can still use the same the chain rule to model that time series.
Hi, Yan. I just wanted to make a brief comment here. So if people aren't used to reading papers and they're not used to seeing this math around like maximum likelihood and the chain rule, if you know how like GPT-3 or other generative models work, then you can use all your intuition from that and you don't have to worry about the math. The main thing here is that when you're at step T and you are going to emit the next piece of data, that is informed by all the T-1 things that you've done before. Okay, so if you have a model that just generates like an image and it generates everything all at once, that's not an autoregressive model. But if you had a model that does one pixel at a time, and by the time you're doing pixel 100, it knows what the first 99 pixels were, that's an autoregressive model. So in this case, what we're saying is we're not going to just spit out the graph all at once, but rather we're going to do one node, add an edge, add an edge, add an edge. And at every step, the model will be aware of all the things it's added so far. So, so if you're familiar with other models that look like that, feel free to use all your intuition from those models.
Yeah. Yeah, so I actually myself really like this idea. Like in the beginning, I thought, oh, the graph structure can be so complicated and the graph can be really huge, right? So how can we model that? So if you think of that graph formulation process just as a sequence of actions, like each time we just focusing on one node and focusing on all the edges related to that node, I think it's a simpler process to understand for the graph generation. Yeah, I think
just
the
a quick question to just a quick question to Ted. I love that explanation. It was very helpful. But it's clear if you have a time series, it's clear what order the generation is occurring in. So it's clear what depends on what. But if you're doing a graph generation, it's not obvious to me that there's an ordering here. So how do I square those two in that context? Thanks.
So I think, yeah, you're going to cover. You can do it naively, and then you can talk about an optimization, right?
Yes, yes. So you can begin in the beginning. You can just do a random ordering of the graph nodes, and later on, if you want to, become more efficient, you will see that they actually use the breadth search first ordering of the graph. Okay, I see already lots of questions related to the following sessions. So let's move on next. So if we are going to model the graph generation process as a sequence, then one most straightforward deep learning model for that is recurrent neural network, right? So you see, it's the network originally, you can use it for time series and to model language processing, right? To model a sequence of words. And yes, you can also use it for graph, like to model a sequence of actions of adding nodes and adding edges. So let's see what's this idea of graph RNN. So the graph RNN idea is you generate the graph while sequentially adding nodes and edges, right? Say we have this graph like 5 nodes. And say in the beginning, we just focus on, say we just randomly pick one node to begin with. So the first node here. And then the next action, say, is to add node 2, right? And the edge related to 2. So you want to add the edge of the new node to the existing node in current graph, right? So the existing node is 1 and the new node is 2. So you want to figure out whether or not I want to add this edge to this node. And yes, so you can add this edge. So you see the action is add a node 2 and add an edge to 1. Right? So that's your new graph. And then the next action will be, well, add a new node, 3 over here. And then you want to figure out, okay, for node 3, do I want to add an edge to node 1? And also, do I want to add a node edge to node 2? It turns out, okay, in this graph, we just need to add an edge to node 1, right? And such moving forward. So at each step for the new node, when we add a new node, we are going to figure out whether or not we want to add an edge to all the existing nodes that are already in the graph. And that is the generation process, right? So each of the time, we just add a new node, and we want to figure out whether we want to add edge to all the existing nodes in the graph. And in the end, so this is a last node in the graph, and then it turns out we just need to add 2 edges to the graph that we already generated. So this is an iterative process. Okay. So I think the process right now becomes more clearer of how we want to, or how we transform the graph generation process as a sequence of action. Okay. The next is, I think the question already raised up about the ordering, right? So, well, in the beginning, you can just choose a random ordering of all the nodes, or it says that the graph with the node ordering pi. So if you given the ordering of the node, it can be uniquely mapped into a sequence of node and node additions. So for this sequence, we can define this set of actions, right? So this is the what we are going to do at each step. So each step as 1 pi. Pi is the node ordering. And we are going to figure out, okay, we are going to add a new node, and we are also going to figure out the edges we are going to add to the graph. So this is a sequence, and this is the input to the model, to the recurrent neural network model. For that sequence, it has 2 levels of sequence. So it's basically a sequence of sequences. So what does it mean? Right, so there's a node level sequence, right? So each time there's a recurrent neural network for nodes, because you add the node sequentially, right? So you want to model that sequence of nodes, and appended to each node, there's also a sequence of adding edges, right? So you want to add edges between existing nodes. And so this is a second sequence. So 1 sequence for the low node adding step, and 1 sequence for adding the edges. So at node level, each step, a new node is added, right? So this tells you at node 1, at node 2, and node 3, etc. So this is node level. And then at edge level, you are going to focus on, okay, whether should I connect it to node 1, should I connect it to node 2, and node 3. And the output, or say the training data, will be, because this will be from the actual graphs, right? So if there is the connection between node 4 and 1, then the data is 0. And if there's isn't a link between, then the input is 0. And if there is a link, then it is 1. So that is a sequence of adding edges, right? So it's do not add a node, link, add a link, or add an edge, and add an edge between node 4 and node 3. So right now we have 2 levels. So one is node level to add this node iteratively, and also at the edge level, we add these edges iteratively. So we can train 2 recurrent neural network for these 2 sequences, but these 2 recurrent networks, for sure, they must be connected. So in the summary, so a node plus a graph plus a node ordering equals a sequence of a sequence of nodes, and also of the sequence of adding edges. And say the node ordering is randomly selected in the beginning, but we will come back to this later on to make it more efficient. And if you view it in an adjacency matrix, so adjacency matrix tells you the rows and columns and the nodes, right? And 1 and 0 are telling whether these two nodes are connected or not, or 1 means connected, 0 means not. So it's basically you are modeling this adjacency matrix. You are at node level, you are moving this direction, right? So at node 2, node 3, node 4, and edge level, you are doing this. You are modeling this sequence, vertically sequence in the adjacency matrix. Okay, so we have transformed the graph generation problem into a sequence generation problem. And we need to model two processes. So one process is we need to generate a state for a new node. And of course, we are going to utilize the state somehow in the second sequence modeling, right, to generate edges for this new node based on its state from the first output. So we are going to use the recurrent neural network to model these processes. So next I'm going to talk about how to do that modeling, but I want to pause a little bit to see if there's any question on this process. Is that clear of like a sequence of sequences?
Yeah.
Cool.
I have a question. Is it also working for directed graphs?
Sorry, working for?
Directed graphs.
Oh, directed graphs. Yes, let me think. Yes, I think so. It's just that action also has a direction associated with that.
Yeah.
Right? So yeah, right now when you add a new node, you need to tell, yeah, so that sequence of edges you need to have kind of double the sequence. So is there an edge like from node 1 to node 4 and also an edge from node 4 to node 1? So you have kind of double the length of sequence for the edge process. Yeah. Okay. Yeah, sure. So since we are going to use the recurrent neural network, yes, for directly graph, the adjacency matrix won't be symmetrical. Okay, so since we are going to use recurrent neural network, so let's just recall a little bit on what is a recurrent neural network. So recurrent neural network is specifically proposed to model sequential data. And the input of the recurrent neural network is a sequence, and you're going to use that sequence to update the hidden states. So just as that auto-regressive model, right? So it's very important to kind of extract the useful information for all the previous steps before time t, before current time step. Right? So the hidden states kind of doing that. So the hidden states is basically summarizing all the information, the input before current time step. So in the recurrent neural network, they are doing that through recurrent neural network cell. So they call it a cell. The cell usually has an initial state input. So it can be a state, say, from previous cell, or it can be just some initial state to kick off the training process. And then it can take the input, say it's the first word or the first action in that sequence. So that's your input, the first input in that sequence, and it's going to give you output. And through the cell, it's going to give you an updated state. So you're going to update the hidden state given this input. right? And yeah, you are doing this iteratively, and actually for all the cell, they share at one layer, right? So this RNN cell for one sequence, this RNN cell all share the same parameters. So this the parameters is going to use again and again, like depending on how many time steps, how many inputs you have in that sequence, and it's basically rolling over and over again to update the hidden states. And in the end, hopefully, what we want to achieve is that in the end, we hope that the hidden states is a good summary of the input sequence observed so far. Okay, so the key components of the recurrent neural network is, so we have the state from previous cell, and we have the input from the sequence, and we are going to give output, and also we are going to give an updated state. So the update, the hidden state, well, the simplest recurrent neural network is this, right? So you can just do a linear transformation of the input, a linear transformation of the previous hidden state, sum it up together, and pass it through the activation function, and that gives you the updated hidden state. And for the output, so it's another just a linear transformation of the hidden state. Yeah, so this is a very simple recurrent neural network cell. Well, there are more expressive cells, as you can see, like the gated unit, recurrent unit, the LSTM, etc. So these are proposed to, so they are adding gates basically to the cell so that they can capture the long sequence better, because people find that when you add in more and more cells, to model the long sequence, it's very easily to get lost. The earlier information is very easily to get lost through this repeated calculation, and it's very hard to train. So people kind of modify this RNN cell so that it can model long sequence better. Okay, so of course the RNN, you can use the very easy simple RNN, and also you can use these advanced cells in this modeling. Okay, now let's see how it's going to apply to the graph RNN. So we have a node level RNN and edge level RNN, and the very important step, I think, is to understand the relationship between the two RNNs. So how they are going to talk to each other. So the node level RNN is going to give the initial state for the edge level RNN. Yeah, so because the node level RNN kind of tells you the summary of the existing graph that you already generated, and it's going to pass on that information to the edge level RNN. And then edge level RNN again will sequentially predict if the new node will connect to each of the previous node. And then the state of the edge level RNN again will serve as the input to the node level RNN. So each of them is basically like updating the state to each other. So we are going to see that diagram later on. So here is one example of the node level RNN. So this horizontal is the node level RNN, and the vertical is the edge level RNN. So say this is so SOS is basically just the initial symbol to kick off the sequential process. So it's just the first symbol in the sequence, say. And then you add one node. And then since you just have one node in the graph, and then basically, there's no need to figure out whether or not to add edges. So you can just directly move on to the second step. So the second step is you add another node. So S2 will be add another graph node. And then you need to figure out whether or not the second node will be connected to the first node, and you say yes. Okay, so there's a new edge connected between these two nodes, and then the output, and then the output of this will be served as the initial state for the edge RNN, and the edge RNN will figure out, okay, when we need add a third node, so the third node, should it connect to the first node? Should it connect to the second node? So the one is yes, it should connect to the first node, and then this is the new graph that we generated so far, right? So the third node will connect to the first node. Again, the state will again initialize the sequence for another RNN for the edge generation, right? For the fourth node. And then again, it's a 0, 1 kind of sequence to tell you which edges to add, and so on. Right? So this is the edge level RNN will sequentially predict if the new node, the node 4, will connect to each of the previous nodes. So since there are 3 nodes already exist in a current generated graph, so it will be like 3 elements to predict, like to see whether this will connect it to the previous nodes, already generated nodes. Okay, so then we will see that, okay, so this is like how you are going to like transform the existing observed graph, like, and fit it into recurrent neural network structure. And then we are going to see how we are actually say if we have this model, if we have this 2 recurrent neural network, then how can we generate a sequence with RNN? It seems quite deterministic at this time, right? So it just outputs 1 or 0, 0, 1, then how can we input some randomness into the model so that it can generate new graphs for us? Well, the idea that is that actually we can think that the output is no longer 1 or 0. Actually, the output can be a probability. So if it's outputting a probability, actually we can sampling from that probability. So here it basically tells you how RNN can be used for sequence generation. So how it's going to generate a new sequence. So usually you are going to give a start of sequence token, SOS, and to the recurrent neural network, and that, remember that cell. So that cell is going to give you output, and you can use the previous output as an input to the next cell. And then how do I know that I should end this generation, or the sequence will move on and on, right? So you can actually introduce the end of sequence token as an extra RNN output. So if the end of sequence token is 1, it means that the RNN will stop generation. So here's the example. So the initial input is the SOS, so it's the initial input, and it gives you the first output in a sequence, and that also becomes the input for the next cell, and that gives you another new output, and starts, right? So this is your new sequence, so Y1, Y2 till the end, when you predict the end of the sequence token equals 1, so it means the end of the sequence. So you see, this is good, but the model is deterministic. So how can we make it a stochastic one? The idea is, instead of predicting the actual 1 or 0, we can actually predict the probability of whether or not we want to add that edge. So instead of 1 or 0 for that, so we can say Y1 right now represents a probability, and we need to sample from that probability. Say the Y1 is the probability predicting of connecting node 2 to node 1 is 0.9, and then it means that it's very highly likely that we will get an edge connection for these 2 nodes. Once we sample from this probability, then we can serve as the input to the second cell. So here is the example, right? So say y is a scalar and follows a Bernoulli distribution. So Bernoulli distribution means p means if value is 1, then it has a probability p, and if value 0 has probability 1 minus p. So it's basically modeling 1 or 0, and getting a value of 1 has a probability of p. Say you give an output of probability, say 0.9, right? And the next step, you're going to sample from the Bernoulli distribution with p equals 0.9, and then you get a 1. And that's your input to the next cell. And again, you give another probability output for the next step. And then you are going to sample from the Bernoulli distribution with p equals 0.4. And this time you sample, you get a 0, and so on. Right, so this is how we are going to like add some randomness in the data, and so that when we get this model, and every time when we sample, we would probably very likely, end up with a different sequence every time when we do the sampling. Even though the probability is different, is the same, but the sampling can be different, right? So even it's 0.9, we can still 1 out of 10 times we can get a 0, right?
Can I ask a question?
Yeah, sure.
Just to understand, the output of the probability is of the first RNN that outputs the node, and then this probability is used for sampling in the RNN of the edge?
Yes.
Okay.
Correct.
Thank you. So for each edge, I need to sample again from the probability of the specific node?
Yes. So for each edge, we need to sample from this. So you can think of this. So this is you can think of this as the edge level Rn, right? So each of the probability tells you what's the probability of that new node connected to node 1, and connected to node 2, and connected to node 3. So this is a probability, but actual whether or not you are going to connect depends on this sampling process.
So the sampling process from the new node, or the node that I want to connect to it, if you understand. I mean, on the RNN.
Yeah, the sampling process is for the edges, right? Say you add node 4, and then this tells you whether or not that is deterministic. So you are going to add node 4. And then the next you want to decide whether or not you want to add the edges.
Yes, but let's say that we are in step 4. We sample, we predict the node 4, and then we have the prediction of 0.4, and then we have to determine the connection to each of the formed nodes.
Yes.
So on this step, I will sample from 0.4, or from the specific each node former probability, the nodes that I want to connect to.
Yeah.
So each time I will sample from 0.4, or from the probabilities of the nodes, the other nodes, not the node that I'm coming from.
Yes, so the other node. So each time you are going to sample from this, say this is the node 4 already added to the graph, and this is you want to sample. So whether or not connected to node 1, you are going to sample from 0.9, and whether or not node 4 is going to connect it to node 2, you are going to sample from 0.4. And to node 3, you are going to 0.3. So each of the edge is going to have a different probability.
Yeah. Okay. I fully understand. Okay. Thank you.
Yeah. Okay. So the next is how can we utilize the training data, that sequence, to train this recurrent neural network? Well, in the training, so one popular way to train in the recurrent neural network is called a teacher forcing. Since it's going to output probability, right? And then, so this star is the actual ground truth labels of that. So this is whether or not node 4 is actually in the training data, right? So node 4 is vector, whether that is actually connected to node 1. So it's 0 means there's no connection for node 4 to node 2, and there is a connection between node 4 and node 1. So this is the ground truth labels. And this is our probability. And you see that we can already compute a loss between the labels and the probability. And the teacher forcing is you just replace the input and output by the real sequence rather than the sampling process. So in the training process, we are going to replace the output and input with the actual labels from the data. Right? So you are going to use 0 instead of 1 because you predict a high probability of 0.9, so it's very likely that you are going to get a 1. But in the training process, we are going to use the actual label 0, right, as the output and as the input to the next cell. So this is a teacher forcing. So it's so it's doing what it says, right? Teacher forcing process in that. So once we have the labels and the one straightforward way, like to measure the loss between the labels and the probability is the cross entropy loss. Yeah, so is basically defined this form. So this is your label and this is your probability output. And you see that when you get a 1 and you want to minimize this, right? You want to minimize this loss. So when you get a 1 label, you want your probability as close to 1 as possible. And when you get 0, you also want this to be as probability as close to as 0 as possible, so that you can minimize this loss. Right? So this kind of tells you the direction of how you want your probability output will be like. So this is your loss in the training process. And so that this Y1 is fitting the data samples, so Y1 star. And this loss will adjust the recurrent neural network parameters accordingly using the backpropagation. Okay, this is your target. And putting things together, so again, this is the overview of this 2-level RN. That each time we are going to add a new node for the node RN first step and use this output to initialize the states for the edge RN. And in the edge RN, you run the edge RN iteratively to predict if the new node will connect to each of the previous node in a sequence, right? So each of the edge, you will get different probabilities from that. And then once that sequence ends, right, so you figure out whether or not you want to add the edges, and then you are going to use the last state, hidden state of the edge RN as the input to the node RN again, and run that for another step. So you are going to pass so the hidden state is passing on between the 2 RNs, right? And that hidden states kind of represent what is the summary of the generated graph so far. So it's an iterative process. So you are going to use the hidden state of the edge RN to initialize the node RN again, and then you are going to run the node RN for another step, and so on. Right? So it's an iterative process. The stop is if the edge RN outputs the EOS as the step 1. And that means there's no edge connected. So you just generate one single node with no edge connection at all. And we will stop the graph generation. So here is the training process. So So SOS means the start of the sequence. So here is the edge RN that tells you whether node 2 will connect to node 1. And then the outputs of the hidden state of the edge RN will serve as the hidden state of the next node RN cell. And then you are going to and the output of the node RN will initialize the edge RN. And then you are going to output the probability for all of this, where node 3 connect to node 1 and where node 3 connect to node 2, etc. Right. And since you are in the training period, you are going to use teacher forcing. So the input comes from the actual data label. So there's no sampling process in the training. You are just directly using the label for the training process. And again, you pass on the hidden states, right? The edge RN and node RN as to serve as the input. And then the EOS. So for the last node, so this is for node 4. And turns out it gives you EOS, the end of sequence. It means that no edge will be added for node 4, and that is the end of the sequence generation process. And for this, and actually we will do this cross entropy loss, right? So we will do the loss like over time, like back propagated through the sequence. And that is the loss that we want to minimize through the back propagation process. Okay, so this is the training process. And for the test processes, you are going to do the sampling, right? So the RN is going to give you probability, and you are going to do a sample from that probability. So say here, gives you a probability of 0.9, you do a sampling, it gives you a 1. And then you pass on to the next node, and it gives you a probability of 0.2. And then you sample from that, and then you will use the actual output and actual input in the edge RN, and so on. Right? So right now at each step, you are going to use the main difference from the training time period is you are going to do a sampling, and you are going to use the actual input and output from the model. Okay, so the quick summary of RN. So there are 2 levels of RN. So you generate graph by generating 2 levels of sequence, and you use the RN to generate that sequence. And we also need a proper evaluation, which we will introduce next. Right? So whenever you think of this graph RN, you can just think of this adjacency matrix that one model is for the horizontal and the other model is for the vertical sequence.
Can I ask a question?
Yeah, sure.
Just maybe, how do I know which node is which? I mean, which node in the true data is equal to every node, to each node in the training?
You mean the node ordering?
Yeah, I mean, it can be like totally random. So
yeah. So right now, say you have the graph. So right now it can be just totally random. Like for all the graphs in the training, you can just generate a random or node ordering for this. But next, there will be a more efficient way to do that. So I will introduce next. Any other question? Oh, okay. So next, I'm going to talk about how to scale it up and how to evaluate the output from the graph generation. So one issue that so far is any new node can connect to any prior node, right? So it can be too many steps for the edge generation. Because previously when we generate that edge RN for the new node, we need to figure out whether there's an edge connection to all the previous nodes generated. So it's really computationally expensive, right? So we need to shorten the sequence. So how can we do that? So how can we limit this complexity, right? So, not, every time when we add a new node, can we just, just consider a limited set of edges rather than figuring out all the connections to all the existing nodes? So that's not tractable to train for the model and not possible to scale up. So one way to do that is through optimized ordering of the nodes. So the people introduced the first is the breadth-first search of the node ordering. Say you start with a random node in the graph. Say you start with node 1, and then you generate a breadth-first search. The breadth-first search is you first always iterate through the neighbors of node 1. So this is the 1-hop neighbors from node 1. So 4 is the kind of 2-hop neighbors for node 1, right? So the node ordering depends on these distances, the hop distances between the graph nodes to this node. Say you add node 1 and node 2, so the next node should be node 3, right? And then the next node should be node 4. And then when you generate a new node graph, node 5, this time, since we know that it comes after 4, and then we know that 4 doesn't connect to node 1, then 5 won't connect to node 1. We know for sure, right? Because it comes in the ordering of the breadth-first search. So the 5 has a minimum hop distance of 2, since the earlier node 4 has a 2-hop distance. So the next new added node should have more than or equal to 2 hop distance to 1. So we no longer consider whether or not 5 will connect to 1. So that kind of limit the complexity or limit the length of the sequence in the edge RN. Okay, so right now we only need to memory of 2 steps. So what are the 2 steps means is like we just need to remember that we add a node 5, and before that, so when you add a node 5, you just need to remember, like previous step we have added the node 4 and the 4 connected to 3 and 2 with that. So we don't need to remember the whole sequence of the in this sequence. So this, of course, will reduce the computational complexity, and of course, it will require the training input to be, to order all the node as this breadth-first search ordering. And it reduces hugely the steps for the edge generation, and that makes the graph generation and also the training much faster. So if you view it in a adjacency matrix way, is previously we need to consider the long sequence because we need to consider whether there's a connection to all the previously generated nodes, right? So if you have a huge graph, then the sequence will get longer and longer. While with the breadth-first ordering, you only just connectivity only with the nodes in the BFS frontiers. So it's not necessarily 3 always, but I mean there's the frontiers, right? So you don't need to consider with the connection to the previous early nodes, right? Because you know for sure that this has a much larger hop distance to the earlier nodes, since it follows the BFS ordering. So there will be a BFS frontier, like in the adjacency matrix over here. And each time we just need to consider this short sequence rather than the whole long sequence. Okay, so that is the how can we reduce the complexity of the edge RN? Any questions so far? Yeah, so what is the change over here is, I think, is in the training side, like when you generate the training sequence for the RN, you need to follow this breadth first node ordering when you train your graph recurrent network. So last is, say we generated a set of graphs, then how can we evaluate the generated graphs, right? Say this is the graphs in the training set, and this is the graphs that we generated with this recurrent network model. So how can we compare them? So we need to define a similarity matrix for the graphs. Well, you can just visually compare them. For sure, there's lots of great tools to just visualize the graphs in 2D or 3D, well, maybe 2D, to just directly visualize, say, the community and the major backbones in the graph. So you can just visualize them and see they are very similar. And the second is you can actually derive various kinds of graph statistics and then compare the distributions of this graph set. So the visual similarity, say the training set is a grid, right? So the input to the model is a grid. So you have lots of, this grid structure. So this is your input. And say the graph RN turns out to be modeling the grids pretty well. And this is the generated graph from these grids. So you see, although you get some tweak and some breaks in the edges, but it still looks like a grid, right? But some other baselines kind of failed to generate the grids if you give them grids data. It's mainly because the assumption in these models is not a grid, right? So they follow some other assumptions. And the underlying processes, the generation process, do not support generating grids. So that's why they fail generating a grid-like graph. So here's another example of community graphs. Say in the graph, there are two major communities. So this is your training set. And this is the new generated graphs, right, from the recurrent neural network. And it seems modeling there's capture the two major community structures pretty well in the graphs. Well, for this type of model, so one model, MFSB models, able to capture the communities since it's proposed to model communities. So that's why it's doing a great job there. Well, the other, if the assumption fails, the model generation just won't approximate very well. So you see the advantage of the graph RN is there's no specific, assumptions, right? It can directly learn or capture the patterns from the data, from the training data. And of course, you want to do it quantitatively, right? So how can we do a more rigorous comparison? Well, the comparison, well, if you can, yes, you may be able to do some direct comparison between the two graphs to see if they are equally kind of comparable or in terms of the structure, but that process is very complicated. So people figure out to just compute the graph statistics, say the degree distribution, the clustering coefficient, right? So, and each of these statistics is a distribution. And then they want to just compare whether these statistics are similar between the two sets. So how can we compare distribution? Yeah, so how can we compare two graph statistics? Well, we can use Earth mover distance. It basically tells you what's the effort of transforming one distribution to another distribution. We are going to see one example next. And if you are going and so this is like two graphs, like 1-to-1, right? But if you are going to compare two sets of graphs, like one set of graphs to another set of graphs, you can use the MMD based on the EMD. So you can still calculate EMD, but you can use the MMD to get one global kind of metric to compare these two set of graphs. So here's the Earth mover distance. So it's proposed to compare similarity between two distributions. And what it's doing is trying to find out what's the minimum effort that move Earth from one pile to another. So you can think of this as the, say, a pile of Earth, and this is another pile of Earth, and then you want to figure out how much Earth I need to, move between this so that I can transform this pile to this pile, right? So if these two distribution, very different from each other, it means a high EMD. So you need to move the Earth a lot. Well, if these two distributions are very similar, then you maybe just move a little bit dirt, and then it will transform this distribution to this one. And actually, when you formulate it, it's a very simple linear optimization problem. Well, you want to minimize the Earth moved. Well, if you sum this Earth along y-axis, you will have this distribution, and if you sum the Earth along the j direction, you will get this distribution. So it's a linear optimization problem with two constraints over there, and it's very easy to solve. I think if you just remember the intuition is enough, just to remember that this is a way to measure two distributions. And if they are very similar, then the score should be close to 0. And if it's very different, then you potentially get a very high score. So that is like a 1-to-1 comparison. And how about set to set? So one set to another set. So you can actually use MMD. And actually this loss is also integrated into many popular TensorFlow models, the loss. There's MMD loss that you can use. The MMD loss is, say, you just, you can use the kernel here, but the kernel is basically just a function, right? So it can be an Earth mover distance, or it can be a dot function, or any function you come up with. So that is one way to measure the distance between two instances. So you can just think of the K as that way. And so here is the X and Y. So X and Y, both X and Y will sample from P. So from the first distribution. And the second term is both of these X and Y will sample from the second distribution Q. And you are going to minus 2 with the expectation of these distances is X will sample from the first distribution and Y will come from the second distribution. So, well, if you think it's very, not intuitive to understand what this means, but say if X and Y is a scalar and if K is a linear kernel, and actually it turns out just this is the square of the difference between these two. So you calculate this and you calculate the expectation is basically the mean operation, right? So you just taken the mean of these differences between the two sets. And that's your MMD. So basically it's calculating the differences between the two sets and taking a mean between that. So you see here is two sets of scalars. And you can use the L2 distance between the two sets, and this should have a higher MMD since it has an 8 over here, and 8 has a very large L2 distance to 2, 3, and 5, especially 2 and 3. well, will have a low MMD since all the elements in these two sets are very close to each other. Right. So basically using this matrix, we can get one overall number to represent how similar these two sets are. And with the Earth mover distance, because Earth mover distance is to compare the difference between two distributions, and on top of Earth mover distance, we can compare two sets of distributions. Well, each element in the set is a distribution, right? So you can compare two sets of distributions. So over here, so you can compute some graph statistics. So this is your training set, and this is your generated set, right? So you can compute your graph statistics. Basically, it's a distribution. So you get one set of distribution. And for your generated graphs, you can get another set of graph distributions. And then you can report your MMD over Earth mover distance as the overall just one number to quantify how different these two sets of graphs are.
Hey, Yan, can I ask a question?
Yeah, sure.
I didn't understand this MMD. I feel like I'm just missing something. So how is this different from just say, if you have three things, just doing the L2 on each of the three and summing them or averaging them?
If you have three things.
Right, like here you show three things in both the numbers and in the pictures, right? You have 2, 3, 5, 8, 2, 3, right? I could just do the L2 loss between 2 and 8, and the L2 loss between 3 and 2, and between 5 and 3, and I could either sum them or I could average them. It's roughly the same thing either way. It's just a scaling thing, right? Is this different than if I just summed up the losses? What am I missing?
So, yes. So this is a theoretical. This is so when you see people, how they implement these functions, this is a theoretical formula, but people, when they actually calculating, they are doing the direct calculations between that. For example, like this, right? So and also the kernel function, I think, because this, I don't know, maybe some form you are not able to get this. Well, you can do the kernel function, but you cannot directly doing a difference of the two elements and get because the kernel function is the transformation of the two elements, right? So map them into a higher space, but you cannot directly do on that top of the transformation, like just directly on the individual space.
I think I'm missing something, because like the Earth mover distance is just a scalar, just a number, right? It's not a complicated thing.
Earth mover distance is just like comparing two distributions. Yes, just one number.
If we have three different statistics and we say, here's the Earth mover distance for each of those three, why do we need something complicated? Why do we need MMD? Why can't we just like sum the differences or something?
You can. So you mean, just do the mutual of this, right? So 2 equals 8. Yeah, actually, when you do this comparison, you are doing that. So you just calculate the difference between 2 and 8, 2 and 2, 2 and 3, and 3 and 8, 3 and 2, 3 and 3. Calculate the differences, square them up, and do a mean of that. That is your MMD.
Yeah,
so the MMD is...
But these are not numbers, these are nodes, no? How to go to, it's not meaningful to compare the numbers. Oh, I meant.
So is the MMD doing, like for three numbers, is it doing like all whatever 6 different comparisons, or is it just doing it position-wise, just 3 of them?
Not position-wise. It's doing all the mutual because it's a set. Set doesn't have any ordering.
I thought it was just doing position-wise, in which case it seemed to me roughly the equivalent of just sum up the numbers.
Yeah, it's a set. It's not a list.
Thank you.
And then this is one example of like comparing the graph gen with some other baseline models, and this is the overall MMD score. Right, so you can see it's extremely well. I don't know what metrics they are using, but it turns out the graph RN is the winner of the winner of 4 for that graph generation process. The gap is very obvious on that. Yes.
I'm not sure I understood how to represent the graph as a distribution. I mean, we saw how to predict a graph. Maybe how to present a graph as a distribution.
Oh, okay. Yeah, so I think I have, yeah. So for example, this is a degree distribution. It tells you like for each of the graph node, how many neighbors it connects, right? So for each of the node, you are going to count how many neighbors that node has. So say for each node, so one node has 3 neighbors, one node has 4 neighbors, and as such. And then you connect all these degrees and then you plot a distribution. And that is your distribution for that graph.
So it's based on the degrees, okay.
Yeah. Based on degree, and there are many other node-based features. I'm sure there are many other maybe edge-based or other subgraph-based features, but yeah, so if it's a node level features such as the degree and clustering coefficient, yeah, you can extract a distribution out of that very easily. Okay. Yeah, so I think that's all of it. I think I make the exact minute of what we promised. And yeah, so here's the summary of today's meetup. Yeah, so we are basically formulating the graph generation process as a sequence generation problem. And each decision is made based on a hidden state. And actually, these hidden states are kind of shared across 2 RNs, one for the node, one for the edge. And possible tasks is it can imitate a set of given graphs, right? So just give the model a set of graphs, and so it's going to trying to generate another set of graphs that's very similar to the given graphs. And also it can be part of the pipeline for optimizing graphs towards given goals. Because right now we have only one goal, right? It's just to generate similar graphs. But if you have some other goals, say to optimize the drug likelihood of the molecules, so how can we also take into consideration? That is another great use case example in the slide. So if you are interested in that, so feel free to look at that. And also that requires reinforcement learning in this and how to guide the graph generation process toward not just generating similar graphs, but also having certain properties that you want to optimize.